More than 95% of Northern California's kelp forests are gone. They collapsed into urchin barrens after a marine heatwave stripped the seafloor bare. So researchers strapped cameras to 3 wild sea otters and sent them into the dead zone. 6 months and 21,000 hours of footage later, what those cameras recorded did not just confirm a decades-old theory. It changed how scientists believe a collapsing ecosystem can still be saved. Along the Northern California coast, underwater forests that once stretched for miles have vanished. Satellite surveys and diver transects confirm a staggering loss. More than 95% of the region's kelp canopy has disappeared since the marine heatwave that began in 2014. The event, known as the blob, raised sea surface temperatures by about 2 degrees Celsius for several years. Kelp, already sensitive to temperature and nutrient supply, could not withstand the stress. At the same time, purple sea urchins multiplied at unprecedented rates, grazing what little kelp remained until the seafloor was stripped nearly bare. What's left behind is not just a visual emptiness. These urchin barrens are ecological dead zones. The 3-dimensional habitat that kelp once provided, shelter for rockfish, abalone, and countless invertebrates, has collapsed. Fisheries that depended on these forests have dwindled. Coastal protection has weakened, as the kelp canopy once helped buffer storm waves and prevent erosion. Even carbon storage, a key ecosystem service in the fight against climate change, has dropped sharply with the loss of kelp biomass. Despite small rebounds in isolated pockets, the overall trend remains grim. Purple urchins continue to dominate, outcompeting other grazers and leaving little chance for natural kelp recovery. The question now looms over both science and policy. In a system so fundamentally altered, what force, if any, can reverse the shift from forest to barren? The answer remains uncertain, and the stakes extend far beyond a single species or coastline. In the 1970s, marine ecologist Jim Estes began a series of field experiments in the Aleutian Islands that would redefine how scientists understood coastal ecosystems. By comparing islands with and without sea otters, Estes documented a dramatic pattern. Where otters thrived, kelp forests flourished. Where otters had vanished, unchecked sea urchin populations devoured kelp down to the rock, leaving barren seafloors. Estes' work introduced the concept of the keystone predator, a single species whose presence or absence could determine the fate of an entire ecosystem. His research showed that sea otters, through predation on urchins, maintained the balance necessary for kelp forests to persist. This predator-prey dynamic became a central model for marine ecology. The logic was straightforward. Without otters, urchins multiply and overgraze kelp. With otters, urchins are kept in check and kelp forests recover. Decades of data from Alaska and later from California reinforced this relationship, but most of the evidence came from broad surveys and indirect measures. Scientists could see the pattern on a regional scale, yet the fine-scale mechanics, how individual otters actually interacted with urchin barrens in real time, remain largely unobserved in California's changing waters. For researchers facing today's kelp crisis, Estes' keystone predator model offered both a hypothesis and a challenge. Could restoring otter populations reverse the collapse of kelp forests in California as they had in Alaska? Or did differences in local conditions, such as water temperature, urchin species, and coastal geography, limit the effectiveness of this natural solution? The need for direct modern evidence in California's unique setting became clear. The Otter Camera Project would put Estes' ecological theory to the test, seeking to capture the living details behind a concept that had shaped decades of conservation science. Inside the Monterey Bay Aquarium's Sea Otter program, a new generation of field research set out to answer questions that satellite maps and diver transects could not. Terry Nicholson, a senior research biologist, led an ambitious 6-month deployment using 3 wild southern sea otters as living data platforms. Each animal carried a compact suite of instruments, a forward-facing video camera, accelerometers to record movement, depth and temperature sensors, and GPS for location context. Over the course of half a year, these otters generated more than 21,000 hours of continuous underwater footage and sensor data, capturing every dive, twist, and foraging attempt across a mosaic of kelp remnants and urchin barrens. The sensor package was built to answer a simple but critical question: what exactly do otters do inside a forest that, from above, appears lifeless? Movement and depth logs tracked the dive profiles and foraging bouts, while temperature readings provided clues about habitat choice. The video lens offered a direct line to behaviors that had only been inferred in past decades. Each deployment was governed by strict ethical and veterinary oversight. The Monterey Bay Aquarium's animal care protocols required pre-release health checks, careful harness design to prevent injury, and frequent monitoring for any sign of distress or abnormal behavior. If an otter's welfare was ever in doubt, the equipment was removed immediately. To validate the footage, researchers cross-referenced otter camera data with independent lines of evidence. Satellite kelp canopy maps and diver surveys established the broader context, allowing scientists to check whether observed otter activity coincided with real changes in urchin density or kelp regrowth. This multi-layered approach, combining animal-borne cameras, environmental sensors, and ecosystem-scale monitoring, ensured that the study's findings would stand up to scrutiny. The result was an unprecedented granular view of predator-prey dynamics inside California's most degraded marine habitats, setting a new standard for ecological fieldwork and data transparency. 6 months of continuous footage from the instrumented sea otters delivered a kind of clarity that previous surveys never could. The cameras recorded otters descending directly into the heart of urchin barrens, bypassing scattered prey to target dense clusters of purple urchins. In these patches, the footage captured a precise sequence. Otters used their forepaws to pluck urchins from crevices, then cracked open the spiny shells with stones carried from the surface or found on the seafloor. Each foraging bout left behind a trail of broken urchin tests, and within days, divers documented a sharp drop in urchin density, sometimes by more than 70% in a single patch. The otters' movements were not random. GPS overlays and dive profiles revealed a pattern of targeted foraging, with repeated returns to high-density urchin zones. This behavior created localized pockets where grazing pressure dropped dramatically. In these newly cleared areas, divers and satellite imagery confirmed the first signs of kelp recruitment, tiny sporophytes anchoring to the rock within 48 hours of otter activity. The effect was not uniform across the landscape, but wherever otters concentrated their feeding, the barren seafloor began to shift back toward a living forest. The video evidence shifted the scientific conversation. Rather than simply asking whether otter presence matters, researchers could now see how the predator-prey mechanism played out in real time. The footage demonstrated that otters do not just suppress urchin numbers at a broad scale, they engineer recovery, patch by patch, through focused predation. Yet the data also underscored that this effect is highly localized. In areas where otters were absent or urchin densities remained too high, kelp failed to return. The camera study revealed both the potential and the limits of relying on sea otters as agents of ecosystem restoration. Terry Nicholson, senior research biologist at the Monterey Bay Aquarium, interprets the camera study's results with measured optimism. She points to the central California coast, where sea otter recovery over the past century aligns with an estimated 56% increase in kelp canopy, the only region in the state to see such a rebound. In these otter-occupied waters, kelp forests have proven more resilient to marine heat waves and urchin outbreaks, suggesting that predator restoration can buffer ecosystems against climate stress. But Nicholson and other experts caution against simple prescriptions. The effect of otters on kelp is shaped by more than predator-prey dynamics alone. Factors like local light availability, the type of seafloor substrate, water temperature, and the composition of surrounding species all influence whether kelp can recover. In some places, even active otter predation cannot overcome poor growing conditions or persistent ocean warming. The mechanism is clear. Otters can create windows for kelp regrowth. Yet this does not guarantee uniform results, and the evidence warns against treating otter reintroduction as a universal fix for collapsing kelp forests. Restoring sea otters to their former range in California now stands as a managed experiment, not a guarantee. Pilot reintroductions are under consideration for both the northern and southern coasts, targeting historic kelp regions that have lost their natural predators. Each step requires careful oversight, federal and state permits, ongoing scientific monitoring, and transparent engagement with local communities. Managers are designing these efforts to test, not assume, that otter presence will drive kelp recovery. Adaptive monitoring plans will track changes in urchin density, kelp regrowth, and broader ecosystem responses, allowing for mid-course corrections if results diverge from expectations. Fisheries. Stakeholders raise valid concerns about increased otter predation on abalone and Dungeness crab, which could affect local economies. At the same time, kelp forests serve as nursery grounds for commercially important fish and shellfish, supporting about 30% of California's fisheries landings. Healthy kelp also reduces coastal erosion and stores carbon, factors now central to climate adaptation policy. The reintroduction question is not just ecological, but economic and social. Sea otter restoration is being framed as a testable strategy, one that must balance habitat recovery, fisheries interests, coastal protection, and carbon goals through evidence-based management. Today, kelp forests rebound where otters thrive, yet vast stretches remain barren despite hope. The camera evidence proves predators can drive recovery, but not everywhere, not alone. As climate pressures mount, ecosystem solutions must match local realities. Restoration isn't simple, but inaction guarantees silence beneath the waves.